So students, now I will discuss about Thevenin's theorem. That is pretty much important while calculating some uh, sources, some sources and some impedances to make it a single source and single impedance. Okay. So Thevenin's theorem is used to simplify a complicated circuit. Okay, and replace them by equivalent circuit just consists a voltage source and a current and impedance. So VTH, that means V Thevenin is the open circuit voltage at the terminals and ZTH is the input or equivalent impedance at the terminals. That means to simplify a circuit, okay. So now look at this circuit. Here you have to obtain Thevenin equivalent at terminal A, B of the circuit. First of all, when you are willing to apply Thevenin's rule, okay, you have to open the load voltage. Okay, what is the load voltage? What is the terminal? So, if the math has been given A and B terminal, okay, if there is a math of circuit given, there is an output terminal. So, in this output terminal, if anyone looks at the output terminal, they will find out the R Thevenin or Z Thevenin. That means the equivalent resistance of the total circuit. Did you understand? Equivalent resistance of the total circuit. Okay? The rules of superposition theorem and Thevenin are quite equal, but the applications are different. Keep on your mind, if there is ZL or RL, that means load resistance or load reactance, they should have to be removed. If there is no load impedance or load resistance has been given, so just throw it out. Find out where are the terminal of A, B here. So first of all, to finding out the Z Thevenin or R Thevenin, particularly that will be Z Thevenin. So in superposition theorem we know, if we, my dear students, as I have discussed earlier, that Thevenin and Norton equivalent circuit. So here I want to solve some examples of our reference book, Alexander and Matthew and study book, Fundamental of Electric Circuit. So as far as we know from source conversion, that if we done this equivalent circuit, there is V Thevenin and Z Thevenin. So the equivalent resistance should be in series in source conversion, in order to just, if you want to just convert it to the current source, that will be in Norton equivalent circuit. In Norton equivalent circuit, current source and the equivalent resistance, that is the Norton resistance, equivalent resistance will be in parallel to the current source. So the both things are quite bit equal, because the Thevenin's theorem and the Norton's theorem are pretty much similar in fashion, or pretty much similar while you calculate or while you just compute this kind of circuits, equivalent circuits. But the basic difference is the source conversion. If we want to just if you just know the Thevenin equivalent circuit, you can easily convert it from source conversion. Just V Thevenin divided by Z Thevenin, that will be I Norton, and that will be in parallel, and Z Thevenin and Z Norton will be equal. Okay, just in source transformation here, it's definitely they say that source conversion. And V Thevenin is the open circuit voltage, while I Norton is the short circuit current. So that is pretty much similar to the source conversion technique. So now just coming to the point that I want to do some example, while you have to example 10.8, that to obtain the equivalent at terminals, Thevenin equivalent at terminals AB. So that is pretty much a hard math for you. but don't be afraid, I will be with you. First of all, the step is that you have to find out the Z Thevenin. So while you want to find out the Z Thevenin, you have to look upon here and find out the equivalent circuit, equivalent resistance or reactance from these terminals. Okay, so if there is a voltage source, you have to make it short. So you have to make it short, so that will not be there. As you can see, I have given it to the short. That will be not here. That will be not here. We have shortened out. Then make it quite simple circuitry. Okay, just keep on your mind that we are doing equivalent circuitry. Okay, equivalent impedance. We have to find out equivalent impedance. So there is a short circuited path, you can see. So if you just redraw this circuit and make it a more simplified circuit, so you can see that if you can just hardly draw a straight line from here, that will be the common point between these two. That will 4 ohms C, and the impedance are here, and these A and B, if you just make A and B from here, that will be A point and that will be the B point. So illustrating this circuit, or make this circuit an equivalent resistance, last of all, if it is shorted to each other, that means these 2 points are common points, and while you find any kind of common points to each other, so the common points will be parallel to each other. That means these points are the similar points. Okay, so we can redraw it. We can redraw that these points D and F point are shortened out. So just make it short and draw like this. That will be a capacitor. That will be the resistor. That is one branch. Another branch, a resistor, and that is the inductor, and these other 2 points are there. This point, and coming back to the solution now. Previously we have finding out the Thevenin, shorting out the voltage. So now here you can see that the points FD point, 2 points. FD, that means the shorted circuitry, and there are 2 parallel ports. First of all, just 8 ohms to 6 ohms. That means 2 branches. That means this 8 ohms and the 6 ohms. If it is shorted, so this point and this 8 point are common points. So 6 ohm and 8 ohm will be parallel, and here also the 4 ohms, this D point and this F point are connected to this 4 ohms and K12 ohms are also parallel. And on these parallel ports, there is a series line, this AB, this line is there, this line.